Friends, welcome to this new video. This is the third of the series which started with damage index. Our main theme is to verify which method out of Codal method and EPBD method is more efficient, more user friendly, more economical. So for that purpose, we started first with the damage index, the theoretical background, etc. Second was the fragility, where in the second video we had discussed the theoretical background. In today's third of this series of these videos, we shall discuss the numerical application for the computation of fragility curves. And we shall see how to utilize the fragility curves for getting the probability of damage or probability of accidents of an event. In the next video of this series, which will be the last one, we shall really go into the comparison based on the damage index, comparison based on the fragility, and comparison based on the economical aspects or cost. And we shall find which method is superior. So with this, let us enter into the video. So we enter into this new video, part 3 of numerical application of fragility. For the purpose of refreshing our memory, let us see the definition of fragility. A fragility function or fragility curve gives a conditional probability that a structure reaches or exceeds a specified damage state under an intensity measure of ground motion. So fragility can be a probability of a damage state exceeding a damage state limit under some intensity measure which is x. So it can be written as phi ln x minus mu by sigma. Phi is standard CDF, cumulative distribution function. Mu is the mean of the natural logarithm of the intensity measure. Sigma is logarithmic standard deviation representing total uncertainty. This is also using logarithm of the intensity measures. The mean is given by this formula, mu, and the standard deviation is given by this formula. N is the total number of ground motion records, which is 22 typically in our case. And Z is the CDF, cumulative distribution function, given by this. Now the intensity measure, let us also see the definition. Intensity measure is a scalar parameter that quantifies the severity of earthquake ground motion at a site. So it can be peak ground acceleration, peak ground velocity, peak ground displacement, spectral acceleration, spectral velocity, spectral displacement, and so on. On the other hand, engineering demand parameter EDP quantifies the structural response or demand caused by earthquake ground motion. The parameters can be IDR, the interstory drift ratio, plastic rotation, maximum displacement, peak floor acceleration, peak floor velocity, and so on. So the first one, intensity measure, is the demand imposed, and EDP, engineering demand parameters, are the output or the effects of that. We have considered a building like this, and the FEMA P695 gives a sortie of 22 ground motions which you have to consider. So these are fixed, you cannot change all this. There are 22 ground different magnitudes given here, and their occurrence of time and place are also given here. Now we are not going to use these earthquakes directly, but we have to make these earthquakes compatible to the design spectrum for which we have designed our structure. So we produce what is called spectrum compatible ground motion. There are several softwares available, including Seismic, which produces these spectrum compatible ground motions. Let us name these ground motions from GM1 to GM22. So these are called the background earthquakes, from which the different earthquake parameters like the frequency content, then pattern of peak ground acceleration, pattern of the ups and downs, duration, etc. will be taken up, and the energy level of the earthquake will be compatible to the design spectrum for which this structure has been designed. So these are your SCGM. Now the design spectrum here is shown by the thick black line, which is Indian code. You can consider any code of your like. So it can be the European code or ASCI given code or any code. Just for typical example, we have taken Indian code, which peak value of acceleration is 2.5, and these GM1 to GM22 are the spectrum compatible ground motions. How to check whether these are alright? You plot these response spectrum corresponding to these earthquakes. These are artificially generated earthquakes, 22 earthquakes, for which, for individual, any earthquake, you can create the response spectrum. So those response spectrum, if you fit in this curve, they should be matching our design spectrum. So more or less we see the match is correct. Now, incremental dynamic analysis is required for getting the fragility curves. The incremental dynamic analysis means you are increasing the peak ground acceleration gradually from one stage to another gradually, and you are reading the nonlinear response of the structure. So the steps I have discussed here: take one SCGM, say GM1, apply it in one direction of the building, say along the short direction of the plan. Run the nonlinear time ST analysis for peak ground acceleration scale to say 0.1 g. You have generated a GM1, which is SCGM, and its peak ground acceleration may be say 1 g, 1.5 g, like that. So all the ground accelerations we shall scale in such a way that its PGA is equal to 0.1 g. So earlier if it was 1 g in the GM1, now we are scaling in the scaling factor by 1/10, so it becomes 0.1 g. So in the software there are dialog box for which you can put the scale. So the ground motion does not change, only the scale changes. Now capture the maximum IDR, say IDR 0.1 g, corresponding to 0.1 g level of the shaking. You find out how much IDR is created in the system. So at every floor there will be interstory drift. You pick up the highest value out of all the floors, all the stories. Then this gives 1 point in my fragility curve. It is IDR 0.1 g and spectral acceleration, say the ground acceleration is 0.1 g. PGA is 0.1 g. Now let us take this ground acceleration to say 0.2 g and again carry out the NLTH, nonlinear time ST analysis, and find out again the point becomes now IDR 0.2 g, 0.2 g. Repeat the steps, increasing the scaling in this way. So next it will be 0.3 g, then 0.4 g, 0.5 g, like that, up to maybe 1 g, 1.5 g, 2 g, whatever you like. Plot these curves for ground motion GM1. All the points I can add up to get the curve. Plot for other 21 GMs. So all the 20 GMs you have to do, and do in other direction also. We have taken the short direction earlier. Now these all 22 exercises to be carried out along the long direction also. A typical idea incremental dynamic analysis result is shown here. So along the x-axis you have the IDR percentage, the interstory drift ratio in percentage, and on the vertical axis you have the peak ground acceleration values. So here it is 0.1 g, 0.2 g, 0.3 g, 0.4 g, up to whatever maximum you have taken. I have just drawn a schematic diagram of the IDA, say for GM1. This way you carry it out for all the ground motions. There is 22 ground motions under GM1 to GM22, and you get the IDA curves like this. These are all IDA curves. So this IDR, interstory drift ratio in percentage, are having different values. Generally we consider up to 1.5% it is immediate occupancy building. Up to say 2.5 or 3% it is LS building, and at 4% we consider it to be starter of the CP building, so it is almost collapse. So 4% IDR, let us say as the collapse IDR, beyond which the structure will not be usable. So let us make the fragility analysis now for this level, that is 4% IDR level. So draw a vertical axis here which cuts all the lines, all the ideal lines at different points, and pick up the points here. What are the points? What are the PGA values of those points? For example, for GM2 here, this is GM2. For GM2, the value is 1.45 G at 4% idea. This value, this point, 1.45 G. So this way, all the idea lines have the cutting points of PGA. All these you shall be capturing. So after capturing, you get these values. For GM1, the cutting point was 0.95 G, GM2 1.05 G, and so on. So all the 22 values of the cutting points, PGA values, are tabulated like this. Out of this, you find the mean of the logarithmic values of the intensity measures, that is PGA, and the standard deviation of the logarithmic of the intensity measures for the table just we have shown. Now there is a Z, the CDF is given by this expression, and from the Z you can get the probability by considering the probability tables. So the Z values are given here and the probability values are given here. For example, if it is Z is 0.65, then you come here, 0.6 line is here and 5 is here, the 0.05. So this corresponds to the 0.65 probability, which is 74.22% or 0.7422. So this way it becomes slightly manual, but we can use the Excel to carry on all this, so that we shall now see. So here different ground motion names are here, and the PGA values we have obtained are tabulated for the 22 ground motions. If you want, you can sort them in ascending order. So this is ascending order, and you take the natural logarithm of all the PGA values. So this column is the natural logarithm ln PGA for all these values, 22 values. Out of this, you simply calculate the mean. A mean of logarithm may be negative also. In our case, this is negative. And standard deviation, by the standard deviation formula, you can also use the Excel formula, STDEV.S, then the range, and it will give you. So this is the standard deviation of the data, or logarithm of the data. Now, these values we have got from the idea curves. At the intersection of the 4% idea vertical line with the idea curves, we got the 22 points. Utilizing these 22 points, we have found out the mean and the standard deviation. Now look up to this tabulation where I have put the PGA values here, then ln PGA values. But here I have not taken those 22, but I have taken everything. 0.1, whatever increments you have used. We have used here increments of 0.05 G. So first it is 0.1 G, then 0.15 G, then 0.2 G, and so on. Up to I have taken 2.1 G. So these are the realistic values for which you have carried out the incremental dynamic analysis. But for finding the mean and standard deviation, only those intersection points of the vertical line in 4% IDR with all the idea lines have been put up for calculation of mean and standard deviation. Okay. So ln PGA, then find the Z through by this formula. Calculate Z through this formula, ln PGA minus mu divided by sigma. So Z may come negative also. And then find probability. For probability in Excel, there is a formula available, norm.s.dist within bracket the value, comma, true. For each of these Z values, you apply this formula and get the probability. So all the probability values are obtained. Then now you plot it in the curve. So this is the curve, which is the probability curve. Along the x-axis you have the PGA values. Along the y-axis you have the probability of accidents. So that curve we have transported here in our PPT, and it is looking like this. Now we'll take a question over there. What does the curve gives actually? For any PGA you take here, say PGA is 1, then go vertically and read the horizontal value 0.6. So when the earthquake comes with 1 G PGA, then your structure will get damaged to 60% at collapse, that is at 4% IDR, 60%. So this is the meaning of the probability curve. Now let us take a question here. Question is, for this system, what is the probability of accidents at PGA 1.2 G? This is the question. So come to the 1.2G. 1.2G line is here, 1.1, 1.2, and see where it is meeting our curve. Then draw a horizontal line and go to the probability axis. So this is the value. So this gives you the probability is equal to 0.92 or 92%. Let us take another question. How much PGA can be applied to this system without exceeding 30% chance of attaining 4% IDR? Is it clear? Our IDR is 4%, which is almost to collapse. So probability of attaining that state of 4% IDR is 30%. So what PGA can attain this condition? That is the question. So let us come here. Our probability of accident is 30%, so 30.3 value is here. From here we draw a horizontal line, then we draw a vertical line, it meets the PGA axis, and the value is 0.6G here. So a 0.6G PGA will produce 30% probability of accidents for 4% IDR or collapse condition. You can have series of fragility lines like this for different IDR values. So one is 4%, another is 3%, then 2%, 1.5%. As I said, 1.5% may correspond to IO level of building, 2% to 3% you can consider LS building, and 4%, 3 to 4% is CP building. So based on the IDR value you take, that is the damage state you consider, you can calculate for what PGA, what is the probability of accidents of that limit state. Limit state are these IDR values at different percentages, which corresponds to obviously certain damage state. So what is the PGA which can create how much accidents of a condition corresponding to these damage states? So different lines you can get, different fragility curves. So I think the concept of fragility curves and the way of constructing the fragility curve has been explained. If you have further queries or questions, you can put in the comment box. Thank you very much for patiently listening to this video. If you find this is useful, please share, please subscribe the channel, please like, and you put your comments and queries in the comment box. I shall be glad to answer those. Thank you.